we present a sparse distributed material point method that can achieve gigascale simulations. We aim to build a system that pursues the following design goals. First, we want to support parallel simulation on both CPUs and GPUs, allowing hardware switch with little or no code modification. Second, we'd like to develop a distributed system that can scale up according to the available hardware. This requires reliable and efficient grid and particle data management and communication. Third, we demand dynamic workload partitioning for better distributed performance and robustness. And finally, we hope that users with different simulation and programming skill levels can easily focus on their interests, ranging from setting up scenes and designing numerical algorithms to exploring novel data structures. These assumptions and design goals lead us to hierarchical architectural principles. We divide the system into 4 layers: the programming model layer, the particle grid data layer, the PIC algorithm layer, and the application layer. The programming model layer focuses on developing device-portable memory management specializations and parallel execution operations. We employ the open-sourced Cocos library for this bottom layer. The particle grid data layer is designed to implement efficient particle and grid distributed data structures. We use the Cabana library for particle-related management and integrate our distributed sparse grid data structure here to enhance the scalability of the MPM system. In addition, the proposed dynamic load balancing scheme is also attached to maintain runtime balanced workload distribution among ranks. Additional supporting components, including diverse constitutive models, particle sourcing, and sparse collision object, are integrated into the PIC algorithm layer to support eclectic simulation design. Users can customize the initial scenario and material setups in the application layer based on all lower layer components. For example, our method supports simulating over 1 billion particles with 8 OpenSSH-connected workstations. To summarize, we design a performant, versatile, and massively parallel MPM scheme. A novel distributed sparse grid data structure with highly efficient allocation, access, and communication. A custom dynamic load balancing partitioner based on particle and grid workloads. And extensive evaluations and demonstrations ranging from scalability tests, partitioner-related comparisons, to large-scale examples. Now let's get into some technical details. First, for distributed sparse grids, we generate a hierarchical block tile cell representation of the simulation domain. We use global mesh to represent the actual position and size of the domain. The global mesh is transferred to a global grid representation according to the resolution requirement. Based on the partitioning strategy, the global grids are divided into blocks and distributed to multiple MPI ranks as their local grids. Each block is further divided into tiles with a user-defined number of cells. During simulation, all valid tiles are registered into an HPC portable hash map for unique 1D array indices. The grid data is stored in an AOSOE manner, with tiles as the outside AOS, to improve the device cache and parallelization efficiency. To extend our sparse grid for distributed systems, we develop 2 types of halo communications, halo scatter and halo gather. Moreover, we propose a dynamic load balancing algorithm to avoid uneven workload distribution among MPI ranks. To minimize each worker's idle time and maximize node memory usage for more considerable scalability. We first compute the workload on each local rank and summarize the whole workload distribution on all grid tiles. Then the prefix sum matrix is calculated for a constant time workload computation in any given subdomains. We iteratively alternate in each direction to perform 1D optimizations to solve the 3D load balancing problem. For each 1D case, we randomly choose one dimension that is never covered in the current iteration. All partition boundaries in the dimension of interest will be reanalyzed individually for a more even workload division. We use 2 representations to compute the simulation workload on each rank, the number of activated grids or the number of particles. MPM has much more particles than grid nodes, making particle-based workload calculation slower. but it dramatically reduces the rank's idle waiting time for uneven particle parcels. This example shows splashy sand with different partition methods and repartition frequencies. Dynamic partitioning methods can accelerate CUDA computation. The particle case outstands this test. Here we compare different partitioning algorithms with multiple ways to assign MPI Cartesian rank topologies. Except for the acceleration brought up by the proposed dynamic load balancing algorithm, we can also notice that MPI rank topologies can significantly influence performance and requires careful initialization. Another elastic toy example also benefits from the proposed dynamic partition method. Our contributions combined enable us to simulate gigantic resolution MPM simulations. We achieve this 8-rank fluid simulation with over 1 billion particles. The average time per frame is less than 5.4 minutes. Now we show the workload on each MPI rank. Here we simulate a massive mudflow. We can observe how fractures accumulated in this scenario. Now we inject more sand into finer grids with a collision shelf in the middle. Here, we throw numerous elastic objects into a playground. Please refer to our paper for more experiments and analyses. Thanks for watching.